Feels good. Get started.
Wait a second. You want to record?
Oh yeah, shoot. Okay, we're good.
All right, let's do it.
All right, hello everyone. Welcome to today's brand new episode of Corecast. I am Tim, your host.
And I'm Sahil. Welcome everybody to a brand new exciting episode of Courtcast. Before we get started, if you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions in the episode. We'll get to them. So without further ado, let's get to it, Tim. So Tim, there's been a lot of physics documentaries and just physics lores about the one theory of physics, that all of nature can just be captured by one thing. And when I watch documentaries even on string theory, it talks about is it the theory that's going to capture everything? But I feel like this episode will kind of fly in the face of that. So I want to turn it over to you and kind of just give sort of the punchline, and then we can work our way backwards. So go for it.
Yeah, I would say that the one theory of everything is sort of this dreams that a lot of physicists, maybe the older generation physicists, kind of strive for. The one true theory that describes nature. However, if you look at our theoretical progress, that actually seems to be not the case. It seems like every theory that we've described so far doesn't fit into this framework. And in fact, we even have an entire mathematical apparatus that was devised around this. And we'll talk about this in more detail. And generally, theories actually don't fall into specific theories. They live in this space. We can call it the space of theories. And from that angle, it looks like the one theory might not necessarily exist. It seems like physics is described by this very complex space and web of theories. And we'll describe what that is. And from that lens, it seems like we might actually be getting further and further away from this idea that there is one true theory that describes nature. So we'll get to the meat of that.
Yeah, no, that's a great way to summarize it. And I think yeah, it's very counterintuitive from everything I've been told. And so yeah, I would definitely am excited to jump into this. So let's start with, you mentioned space of theories. I think that'll set up nicely the whole groundwork of this discussion. So can you describe what space of theories is, and what is the significance of it? I haven't heard of this when I was learning physics. It's a very new concept to
Mm-hmm.
myself. So go for it.
Yeah, I think it starts with a little bit of historical lessons in physics. We know that back in the days, people studied Newtonian physics. Like Newton discovered that apples fall to the ground. And then if you learn the history of science, you'll know that Newton was wrong and Einstein proved him wrong and discovered the theory of relativity. And a kind of very naive reading, if you were to turn that into a movie, it would be kind of dramatic, right? Like Newton discovered one thing, Einstein comes in, completely trampled that and throw it away. And in the future, we'll probably have quantum theory of gravity, and somehow Einstein's theory will get completely trampled once again. But that actually is not the truth, because in modern physics, we realize that even though Newton was wrong, his theory wasn't useless. Because when we're walking around in our day-to-day life, when we're analyzing sports events, looking at how car machines work, well, we use Newton's theory. So what gives? In modern physics, we have this idea that theories doesn't just trample over one another. Theories actually subsume one another. And we create this more abstract entity called the space of theories, and there are many different names. I don't actually think there's a formal name for that, but in any case,
Mhm.
in our episode, we'll call that the space of theories, right? So you can
Mhm.
think of Newton's theory as a location in this space of theories, right? And Newton's theory is a way to approximate gravity. Let's say apples falling from a tree. Einstein's theory is also a location in the space of theories. It also can describe apple falling from the tree, although much more complicated. So both theories are valid approximations within their realms of approximations. So this more nuanced understanding is that nature can and should be able to be described by multiple theories in this space of theories. And then with this lens in mind, it turns out that every single theory we've ever written down fits into this framework. It's a location in the space of theories.
I see. So one thing about that is I'm wondering like the usefulness of this. You've described like there's this abstract space in which theories exist, and like you can relate Newton's theory to Einstein's theory in some way. But I guess like how it's kind of like Newton's theories like actually can we start like by describing what is the space of theories like like how do I relate this to like my intuitions about like physical space? So like two points can be said to be close together if like their distance is close. So like in theory space, like is like Newton's theory and Einstein's theory like close together? I'm just trying to like conceptualize this abstract space a bit more.
Yeah, certainly. Um, so so if you only care about the concept of it, yeah, the space of theory is very abstract. But you can make it very concrete. For example, Newton's law, if you study physics, has a gravitational constant, right? Has this Newton constant, and you can you can kind of imagine a universe where this Newton constant could change, right?
Mhm.
And then by changing this constant, you are exploring the space of theories. So you can also modify Newton's law to say, in high school we learned that the forces between two massive objects goes like 1 over the distance square. Maybe we'll
Yeah.
add some correction term that goes like 1 over the distance. I don't know. We can add some terms that goes like 1 over the log of the distance, right? Or maybe we can add some terms that links to the velocity of these objects, right?
Mhm.
So you can make the space of theories very concrete. You can just write down, equations where the coefficient of each of these terms is kind of a location of your space of theory. So you can think of it like that. Then Einstein's theory will tell you something about these forces. Newton's
Mhm.
theory will tell you something about these forces.
Mhm.
Sure, they are different in many cases, but if you zoom
Mhm.
out, if you look at the forces between the sun and the earth, they're
Mhm.
close enough, right? So in that sense, we can say, hey, look, even though Einstein's theory and Newton's theory may be different locations in the space of theories, they're
Mhm.
actually the same theories when describing a fixed set of physical phenomenon within certain errors, basically.
Hmm. So are you saying like if I imagine this abstract space of theories, they're like these different points. I don't know if I want to call them points, but for lack of better words, like I'll just say points right now. There are these points that correspond to like say Einstein's theory and Newton's theory, but in like different regimes of whatever you're studying, these points can change distances. So like for instance, if I were to look at like, the gravitational force between sun and earth, Newton's theory and Einstein's theory basically like, are I don't want to say identical, but like, are close enough to each other that you could pretty much just probably get away and use Newton's theory. Maybe if you wanted to do smaller corrections of other things, you may need to invoke general relativity, but for all practical purposes, you can use Newton's theory. But if we go to the regime of like a black hole, for instance, Newton's theory probably like fails, or at least fails for like most things of interest.
Right.
So my question is like you would say, depending on the circumstance, this like abstract notion of a distance between two theories in the space of theory would change. Is that a fair statement?
Yeah, I mean, you could come up with some distance in this space of theories, but it's not very meaningful. And I would emphasize one thing: like this space of theories, it depending on your philosophy, but I think largely it's an artificial construct
Mhm.
because imagine you're Mother Nature. I don't like to bring into discussion this concept of deity, but imagine like such a thing exists. It's not the kind of deity the human can conceive. But imagine
Yeah.
there's some deity controlling the universe.
Mhm.
That deity probably wouldn't care about the space of theories. it just is controlling nature, right? Nature is nature. Doesn't care about
Yeah.
it doesn't care about Newton's gravitational constant. No, no, no. The space of theory is more like a model. Like maybe it's like the Lego movie, you know? Like we using our human minds, we come up with these Lego cities that kind of approximate our real world. And of course,
Mhm.
you can change the kind of Lego blocks that you use, right? You can use smaller Lego blocks, larger Lego blocks. Some of the Legos, some of the models will do a better job than looking like the real thing, and some
Mhm.
will do a worse job. And actually, they do different jobs, right? Like I might be able to build like a Lego Empire State Building really well using one type of Lego block, but maybe the Manhattan Bridge will look terrible, right? So it's kind of like that. So our so this view is kind of like a very humbling view, kind of. It tells you that, hey, look, any theory you got, it's just kind of some toy model that tried to approximate nature. Nature is like superior in every way, but we got our little Lego blocks so that we can play with it.
Yeah. Yeah, yeah. Okay, that makes sense. So I guess maybe it's very different than like think of it like in Euclidean space or how I think about like, the 3+1 dimensions that I live in. To me, that analogy actually breaks down, which is useful to know. But I want to jump to the next thing, which is
Hmm.
you described what this is abstractly, but I guess like so what? Like how is this useful? Like why do we even consider this? This seems to introduce more problems. Like this abstract space, these two theories may not be close in certain circumstances, close in others. But yeah, can you break down like how this comes about and why it's useful?
Yeah, I think I'll first go over historically why it's useful, and in fact, it won a Nobel Prize. So I wouldn't say a Nobel Prize is the arbiter of whether something is useful or not. But look, it's worth something, okay, and at least it's worth a Nobel Prize. Let's put it at that. Um,
Fair enough.
and first I'll go over historically why that's useful, and then like practically why that's useful. It turns out to be tremendously useful. Um,
Mhm.
so we'll hold that thought. So let's go over historically why that's useful first. So people back in the days when they first started studying quantum field theory, they were very confused. Um, what I mean by that is you can use quantum field theory. You can try to compute things like what's the charge of the electron, what's the you can calculate or what's the constant for electromagnetic forces, right? Like the proportionality constant that dictates how opposite charge attracts each other. And when they do calculation, what they realize is that they get nonsensical answer. It's like they get some infinity, something nonsensical. They're like, well, what the heck? Like the theory is giving us nonsense.
Mhm.
And, and the resolution seems to be that look, these constants are actually not constant in the sense that there's an absolute definition. Because like, look, what is the charge of an electron? The only way we can describe it is to look at the forces between opposite charge objects and see how they repel each other according to the 1 over r squared law. So anyway, to measure the charge, it's done through some experiment. So people found out that you can actually describe the same phenomenon using different charges and then adjust the other parts of your theory to make it work. So and then from that angle, actually there is no fixed electric charge. There's a variety of charges that you can use to describe the same physics, assuming that you adjust all the other bits of your theory accordingly. And this
Mhm.
seems very confusing in the beginning. Like how can there be how can the charge of an electron be ambiguous? That's crazy, right? Like it's a
Yeah.
charge, we measure it, right? But it turns out
Yeah.
that when you vary the charge, you're just using slightly different theories in the space of theories to describe your physics, but the physics is the same. And
Mhm.
to relate them together, people introduce this concept called renormalization, right? This is the concept that look, if you insist on giving electron a charge, then this charge depends on what theory in the space of theory you are using to describe it. And depending on the circumstances, you might choose a slightly different space of theory, right? Like for example, if two even electrons and a proton is very close, you might choose a theory that's a little more specialized in dealing with very close things versus if they were
Mhm.
further away, you might modify your theory a little bit so that they're a little so it's better. It's more apt at dealing with things that are a little further away. But if you compare those two theories, like all these numbers are a little bit different. Like the mass of the electron gets a little different. The charge of the electron gets a little different. So using the language of the space of theories, people start to make sense of this now. Like it people start to understand, hey, like it's okay that these fundamental concepts we think are absolute are actually not.
So are you referring to like, so in like, let's say electromagnetism, people assume that, oh, the charge of an electron is, in some units plus minus one, or I mean plus one or minus one, depending on the convention. And what you're saying is like it can actually be different depending on how you measure it. And the way in which that charge changes is like exploring a slightly different theory in this space of theories for electromagnetism. But ultimately, I'm still trying to understand like how this is like useful, how you can like use this, for instance.
Right. Yeah. So we can go a little bit in detail. So the plus or minus one, it is a convention, but beyond that, there's so you can run an experiment. You can say, hey, I have an electron and a proton. I
Mm,
put them, let's say, 1 millimeter apart, and I
yeah.
look at the forces between them.
Mm,
So if I halve their distance,
yeah.
the forces will quadruple, right? And the
Uh,
coefficient, yeah, and something like that. And the coefficient on how that changes is what we call the coupling constant. And in different conventions, you call that the electric charge. Sure, but we can debate about that a little bit. But sure,
mm,
let's use that as the coupling constant, right? So
mm,
if you do this experiment at 1 millimeter,
mm,
and by the way, this is experiment, so it has nothing to do with the space of theories. Okay,
mm,
if you do this at 1 millimeter, you actually get a
mm.
different answer than if you were to do it at 1 micron, and it will be different than if you were to do it at one, I don't know, like femtometer, right?
Yeah,
So
yeah.
so yeah, so the truth is that it's telling you that, hey, your law,
Mm,
your law where it says the force between positive and negative charge goes like 1 over the distance square, it's wrong. It's just telling you that it's wrong because it varies more than that. But if you
yeah.
insist that it's correct, because that's what your theory tells you, it's 1 over distance square. If you insist that your theory is correct, well, you can make it correct by adjusting the parameter a little bit so that it
Mm,
describes that current situation there, right? So there's these two perspectives, because like, look, your theory is never going to be perfect.
yeah.
Given your theory, you're gonna try to do the best, right? The best you can do is you gotta adjust these parameters. So um um so the fact that the electric charge changes, you can think of it as an imperfection of our theories, and in
Mm.
order to accommodate, we kind of need to adjust the charge and masses a little bit.
S- So one question that comes to mind is like, let's say you had a theory at like smaller distance scales,
Mm-hmm.
um, that predicted this, to reasonable level of accuracy, whatever that accuracy is in by particle physics standards. And then why can't you make like, if you want to, let's say, approximate what is that force or whatever you're trying to compute at like longer distances? Why can't you use like long distance approximations theoretically and like say, oh, this term and this term are zero, or like, these set of terms don't really matter in the grand scheme of things, much like how you would go from like general relativity to classical mechanics or Newtonian mechanics by making like a whole bunch of approximations and saying like, oh, these terms don't really matter. These complicated terms like don't contribute to anything really. So I'm trying to understand like what is the benefit that you get from like saying, oh, I guess like, my electric charge is like different, but like, well, yeah, I'm just trying to understand like what the, that approach, or are those the two approaches that you're talking about?
Right. Yeah. I mean, this is just one example, and of course,
Mm,
you play devil's advocate, but like, well, what's the point? Okay, why don't I get a more exact answer? Why
mm,
deal with this approximation? Well,
yeah.
the truth is that every theory is approximate. You can't
Mm,
get away around that. Let's say you fix the problem of the 1 over r squared. You make it a little more precise. Well, something else is going to break now. It's whack-a-mole, like something here, yeah, the other thing is going to break. So kind of the philosophy behind thinking about space of theory is to let go of this insecurity about, hey, look, my theory is not exact, blah, 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 there's these error term here, and just embrace it. Like, it's okay your theory is wrong. Because, look, no matter how hard you try, your theory is still wrong. It's never going to be perfect. Because that's the nature of modern theoretical physics theory. And the philosophy behind the theory of renormalization and dealing with the space of theory is that it's just to accept it, but systematically look at which part is unimportant and focus on the bits that are important, right? And that's the philosophy. When you do that, you simplify your life a little bit. It's almost like, I don't know, like, people have anxiety. It's like, oh my God, so many things going on. I guess renormalization is kind of like the theory's way of meditating on it and just let it go. So, and it just Zen appears.
Oh wow! How that was Zen of you, but I don't know enough about Zen to maybe how come it may not be very accurate. Okay, so you mentioned the word renormalization, and I also want to touch upon like what we started off discussing in the beginning of the episode, that there can be multiple theories that can describe nature. So how do these two concepts relate to each other? Renormalization, I know, is like from way back when I was learning physics as a way to like quote unquote tame infinities, but when you don't no need to touch upon that part of it. But how does it pertain to this discussion?
Yeah, basically, the infinity is, once again, arises because people's insistence of having an absolute quantity. And that happens all the time. But in physics, anytime we get infinite answer, it's the physics way to tell you, be like, hey, look, guys, you asked the wrong question, and you don't deserve a proper answer. So that's literally what it is. And the moment you try to give up on this notion that there is an absolute theory, that there needs to be an absolute mass or electric charge for particles or other properties, like the charge and the mass is just examples, right? The moment you let go of that, you see that, hey, look, every property is relative. And you cannot describe the property of something without saying what location in the theory of space you're using it to describe it. So there's a lot of fuzziness now for properties of these particles. And of course, like in our everyday life, we don't exactly see it, but because this fuzziness is so small, right? This error is so small, so we don't care. And in quantum physics already, we know that there are these fuzziness everywhere. So getting back to the question, yeah. Infinity is really just saying that you're asking the wrong thing, but once you give that up, once you embrace that, like the charge of an electron there could be multiple different ones depending on how you want to describe the system. You pick a different charge, and that's okay, right? And then in fact, we see a much richer structure. So sometimes, and if you embrace that, you can say, hey, look, depending on different phenomenon, I'm going to choose a slightly different theory, and it might give me better answers than if I just focus on one absolute theory. And that's actually very powerful, this concept.
So I guess like how does this pertain to there being multiple theories? Like how does renormalization allow you to like relate I guess different theories that may describe the same phenomenon but at different scales?
Yeah. So very good. Renormalization is just a buzzword for saying, let's say you give me the same physics. Let's say we're describing electrons. There might be 10 different theories in the space of theories that can be used to do that. There's a relationship between every 10 of these theories because the physics is the same. The physics can't be different. The theories can be a little different, but remember, theory is just a construct of our minds, Like 10 different physicists might come up with 10 slightly different theories. Renormalization is a relationship between them all. And we can be a little more concrete. like for example, take water. Okay, water, depending on the temperature and pressure, can look very different, right? Water
Mhm,
can contain water waves.
mhm,
Water can turn into ice. Ice can
yeah,
have sound waves in a solid,
mhm,
or water can turn into water vapor. And the
mhm.
waves in water vapor is just conventional sound wave in air, right? So you can try really hard to say, look, I just want one theory to describe water, and I want that theory to work in all three cases.
Yeah.
You could, you have a supercomputer simulate the particles. Go ahead. I
Mm.
mean, tough work, you know. Or you can say, look, guys, like let's just have three different theories. You know, one describing water, one describing
Mhm.
ice, one describes water vapor, and they are linked by renormalization. Renormalization is just the relationship between them, like how is how are the parameters from one theory related to the next, right? And so that's powerful. Like imagine we didn't know that water is made of water molecules, and we only know water, ice, and air and water vapor. But then we
Mm.
discover these relationship, like renormalization relationship between them. Well, then that's interesting. Maybe we'll be able to discover that there's a common denominator between all three. There's water molecules. So that's kind of where we're at.
I see. I see. So what you're saying is that like water, for instance, can be in these three different phases of matter: solid, liquid, and ice. Sorry, solid, liquid, and gas. And these correspond to three different points in the space of theories for water, for instance. And so you can use this process called renormalization to go from one theory to another theory, kind of like a sort of flow, or like I think of it like you have 3 points in this abstract space. You have this like line that connects all 3 points and has like this, I don't know, direction. Is that a fair analogy, or is that
Yeah, sort of. Yeah, so there are links between these three theories, but one should be a little more technical, right? It's not exactly like you can go from water to ice, although you could if you freeze it. But in the space of theory, we imagine there's one common theory that
Mhm.
says water molecules, and
Yeah.
depending on the circumstances, this
Mhm.
theory can flow into three possibilities. It can flow into the theory of ice, the theory of water waves, and the
Mhm.
theory of water vapor. So it's like a
Mhm.
fork, right? There's a I guess in terms of water, there is the one theory of water molecules we know, and it can
Mhm.
fork. It's like a source. It's like I don't know. It's like a garden hose. You turn on the garden hose, it splits into three, right? Then it's
Mhm.
able to describe all three. You're able to water all different parts of the space of physics, right? You're able to describe them. So it's kind of like that. It's like a sprinkler, sort of.
I see, but doesn't that imply that there's like this one theory and just we haven't worked hard enough to like get to that one theory, or like what? Yeah, I just want to understand that more because it seems like you have one
Mm-hmm.
source and it's emanating these like three different theories, and we just can't get to that like one source. Is that a fair assessment, or am I missing
Um,
something?
I would say people do sort of believe that, but then if you
Okay.
zoom in, you see that the theory of water
Mhm.
actually comes from the theory of more fundamental particles like protons and electrons,
Mhm.
right? So you see that the theory of particle physics flows into the theory of chemistry, and it flows into the theory of water. So it's kind of like turtles all the way down. If you kind of zoom in, you see like, hey, look, guys, what we thought was the faucet, well, it turns out to
Mhm.
be another pipe, comes from somewhere else.
Mhm.
And if you zoom in, it's yet another pipe. So
Mhm.
far in our journey in theoretical physics,
Mhm.
we've just keep finding pipes. We've never found a true source, I would say.
I see. I see. And then slightly more technical question, but I hope it's not too technical. The parameters of these theories is how I think of how you can describe a theory based on its parameters. Would you say that like the parameters vary based on like for let's say water for like temperature and pressure? So you have like this one theory of water, we can only like capture the instance, whether it's like solid, liquid, or gas, and then we have the parameters of whatever theory we're going to use based on solid, liquid, or gas. And you can like make this kind of one theory that happens to like have all the parameters from all three theories, but they're not, but some of the parameters are like zero depending on which regime you're in. Is that a fair assessment? Or
Yeah, kind of. I would say the parameters in theories,
mm,
they are, there's a bit of a debate. Like
mm,
some people think they're physical, and some people don't
okay.
think it's physical. But
Mm,
I would say my feeling is that it's a mix of both, right?
mm,
Some of these parameters are not physical because, remember, the space of theory is a figment of our imagination,
yeah.
right? Like there are these numbers that I put in.
Mm,
Imagine the space of theory is some calculator or Lego buildings, right?
mm,
It's an instruction for us to construct something that looks like nature, right?
yeah.
So of course that instruction is just in our minds. But of course, once we build that construct, the construct has some relationship with the real world, right?
Mm,
Like if my theory has to describe how water waves moves,
mm,
well, it better be related to the speed of water waves. So in that sense, some of the parameters are actually physical in that way because they're linked to physical things. So it's a little bit hard to interpret. But I will say this:
yeah.
the parameters can be very deceiving. Um, in sometimes, because your theory can says one thing, but the underlying physics can say something totally different, and that I don't know if I want to go into details, but sometimes that happens, right?
Gotcha, gotcha. We have an audience question. If all the phenomena in our universe are connected, why shouldn't there be a theory that describes it perfectly? Doesn't symmetry hint at an absolute description, perhaps possible for humans to find?
So again, there are perspectives, right? Like we have believed it for a very long time, but it looks like every theory that we have, first of all, are never exact. Even string theory, it's impossible for you to calculate something perfectly. Like even if you believe the theory is correct, you cannot get an exact answer in many cases.
Mm,
So it depends on your perspective. If you cannot get an exact answer, is it fair to say that the theory is exact or is it not exact? Um, you
mm,
talk to some, they might believe that, hey, look, the theory is exact. It's just humans are too bad. We couldn't calculate it. Or you can take the practical perspective. Hey, look, our answer is actually never correct. The theory is what it is, and kind of
mm,
take this humble perspective. Like look, these theories are just, we build an image of universe. It's our best attempt to approximate it, and
mm.
chances are we're not there yet. Um, and then if you keep going on that realm, you ask, well, is it ever possible? Like, is it ever possible the universe to almost like discover itself exactly? I don't know,
Mm,
right? I guess I'm not gonna make a statement on that,
mm,
but I think if you think of it from a pragmatic point of view, every single theory we have created has a
mm,
level of approximation, has a level of ignorance, and it
mm,
seems like embracing it has helped us more than it hurts us. So
mm,
maybe from that lens, it's still a great ideal to have, right? To believe in the one theory, but maybe
mm.
practically we actually embrace the space of theories opposed to the one theory.
I see, I see. And then one thing that was very interesting when we were discussing this episode is like more, I mean, so far we've been talking about particle physics type applications, but you also mentioned there's like a myriad of like more like real, I guess I don't want to say like real life, but more like more everyday type of application. So maybe you could touch upon that. Be interesting to our listeners.
Yeah. So indeed, like the theory of renormalization has slowly crept into other fields that physics find application, and in biophysics, in some of the societal phenomenons,
Mhm.
people are able to apply this broad technique of renormalization, even in pure mathematics, because the
Mm,
concept is so how do I say it? It's so enticing, right? It's embracing our ignorance and also quantify it exactly to be how much ignorance we have, and how do you
Mm,
shift your ignorance from one place over another and kind of mold your theory to go around it. And
mm,
and for example, um, you can look at stock behavior. For example, you can argue that stock, the way stock goes up and down, fundamentally it comes from these little behaviors of humans. Humans are making decisions. These are the atomic bits of the
yeah.
stock behavior. But you can describe stock by zooming in or zooming out a little bit. You sum
Mhm,
up, different, you sum up the transactions of 10 people, then you get a
mhm,
slightly different picture, right? If you zoom out a little bit more, you get yet another slightly different picture.
mhm,
So depending on how you zoom out, you can always modify your theory in different ways. So it allows you different ways to analyze the stock, for example, and you can apply
mhm.
similar techniques to, like, I think migration patterns or whatever, the emergent phenomenon generally. When you have
Yeah.
like birds, individual birds coming in, but when you zoom out, you get flocks and whatnot.
Mhm.
And I think recently, it's even gotten maybe some starting to get some traction in the AI field, I think.
Mm. That that is very interesting that this is like very tantalizing, but it also makes sense. Um, yeah. Any other applications before we move forward, or anything else?
Yeah, I would say that, like, this is one of the instances where the physics, it just makes sense because it's so practical
Mhm,
that it just lends itself to application in different areas. And now I was mentioning AI. You can also view AI as something interesting emerging out of something that looks different fundamentally, right? Kind of similar to how, if you take the theory of water molecules, you
mhm.
would never have expected that they would create, like like snowflakes. And
Yeah.
snowflake has very intricate structure, like pentagon, hexagon shape with a fractal-like
Mhm,
structure. But if you are able to kind of, and the reason why it's really hard to see that is because if you just focus so hard on the original theory,
mhm,
the equations are so complicated. It's hard to derive anything. But if you kind of just
mhm,
zoom out, be like, let's take a walk down theories, the space of theories. You can see, hey, if I take a walk, I can see how the theory molds and change, and then the
mhm,
appearance of the snowflake will become more evident because once
mhm,
you see that, oh, ice can form, water can form, and stuff like that. And this is very interesting because in AI, recently the large language model is all the rage. You know that fundamentally AI computation is just multiplication and addition, right? And these are kind of like the
yeah.
atomic units of it. But then if you do more and more of them, you zoom out,
Mhm.
some sort of patterns emerge. I mean, I'm not an expert in that, so I can't speak to that. But it's very tantalizing. I'm pretty sure that there could be applications there, but I don't know the details. Um,
Mhm.
yeah. So I would say just leave it at that for now.
Fair enough. Fair enough. And then now I want to kind of jump to some more speculative questions to gauge your thoughts on this.
Mm-hmm.
So you mentioned that, like, in response to our audience question also, that like all theories are effectively effective. There's no like absolute theory or no like true theory. Every theory we concoct will so far probably in foreseeable future will be approximate. And so is this like a limitation due to the language that we're using to describe theories, and consequently the space of theories with just math itself?
Um, this is a great question. I would say it's plausible. I don't know what the answer is, but
Mm,
let me just cover one part. When we take a walk in the space of theories, you
mm,
can distinguish two types of theories:
mm,
ones that are useful and ones that are useless, right?
mm,
Uh, there are many theories that are just so arbitrary. Like for example, imagine you write down the forces between two particles
mm.
next to each other, right?
Yep.
You can say, well, the force depends on the distance.
Mm,
But then you can add many other terms. Maybe you can say that it also depends on the time of the day. It depends on the
mm,
relative velocity. Maybe it depends on a bazillion other things. Maybe it depends on infinitely many things. It depends on tiny, I don't know, whatever you can come up with, right? Maybe it depends on all the histories that the particle has experienced. Now
yeah.
imagine a theory like that. That
Mm,
every interaction, every time I move my finger, it depends on the entire history of the universe, whatever. Well, that theory is kind of useless because I can never know what's going on because you can always fit. Like imagine a theory like that. You can always fit it to all the possible experiments. Like just think of all the experiments we've done.
yeah.
Uh, trillion, I don't know, a trillion experiment. If my theory has a trillion numbers, I can just fit
Mm,
it to all of that, and it will fit all the experiments because physics ultimately is an experimental science. I can say,
yeah.
hey, look, my theory predict everything, but
Mm,
it's useless, right? Because it's got infinitely many numbers. So, so you can speculate and say, well, what if, like, what if, imagine there's a deity.
mm,
I'm going to bring that up again. What if,
yeah.
what if that deity is playing a prank on us, right? Like,
Mm,
like the reason, maybe the reason the sun comes up tomorrow is nothing but a facade. Maybe
mm,
the day after tomorrow the sun won't come again. Maybe there
yeah.
are trillions of parameters in our theory that perfectly predicts every single move until it doesn't.
Mm,
Well, then that's too bad because that's a possibility. Nature could be like that,
mm,
but then that will mean that it's useless. That means like our I don't know, like it means that our approach is kind of useless, right? Um, so in some sense, we hope that it's not true. We
mm,
hope that the space of theories, we hope that this part of the space of theories are not important for us, right? These are
mm,
the useless part. We hope that physics is only described by the useful part of the space of theories.
mm,
And the reason may be that because people have a conviction that there is the one theory, and that's why you
mm.
know the space of theories, useful theory, is so narrow and clean, basically. Um, but I don't know. I don't know, right? This is a hope, but we don't have an answer yet.
Fair enough. I mean, it's a very loaded question. I guess kind of maybe a more extraterrestrial question is do you think aliens would come up with this concept, like other intelligent beings? Um,
Yeah, I feel like if aliens perhaps could, maybe they are smart enough that they won't have to deal with space of theories, right? Because space, or maybe they'll have a slightly better space of theories. It's hard to say. Um, I think maybe they'll just have like a different kind. This is totally speculative, by the way. I know nothing of astrobiology, but it's just
okay.
imagine, But if I were to make a sci-fi movie, right, completely, no science in it whatsoever. But if I were to make a sci-fi movie, I
Okay.
imagine, yeah, I would imagine the aliens will have some kind of quantum computing capability. Maybe they can
Yeah.
perceive infinitely many numbers and subtle relationships between them all at once. Maybe they don't need the space of theory to describe things. They'll just be like, whoa, gee, here's some quantum mechanical stuff, and that's just what it is. They don't even need to write down an equation to describe the physics. Maybe it's a human desire. So maybe in that way, their space of theories will be more advanced than ours, right? So
Yeah. But it seems to me that if you had aliens, like they can't fit all the bits or quantum bits of the universe like in their head, as far as I know. So I don't know, unless the aliens were the universe, they can't really see like any being knowing everything. And so there's some level of ignorance, maybe less than us, but some
right,
mockasm of ignorance.
yeah, maybe I'm not giving humans enough credit. Maybe we do a pretty damn good job. Maybe their space of theory would just have they'll chase down a few more of these sprinklers and kind of maybe get slightly closer to the source, but not quite. So
I
they.
I mean, it's possible the space of theory for aliens could be worse. All right. So, I guess one question that I have on my side, maybe this takes us down a rabbit hole that we can save for another episode, but you mentioned like we mentioned this in past episodes talking about gravity, and especially in this episode talking about like how these things are relative when you try to measure things that are absolute to measure absolute things in your theory, you tend to get infinities. I understand that. But then you say, oh, like relative to, some background or something else, it's actually a finite number. That's what I've seen. But with gravity, as you've said before, it's absolute, so you can't do anything relative. So where do you think gravity lies in the space of theories? Like, is it just off at infinity, or like what do you think about that?
Yeah, great question. I mean, at the end of the day, gravity is the king. So if there is the one theory, it has to have gravity, and gravity has to be the differentiator. Um,
Mm,
we do know that gravity does fit into the framework of the space of theories. Like in the beginning, we talked about Newton's theory of gravity. It's a
yeah.
theory. It's
Hmm.
not 100% accurate, but it's pretty good. There's
Hmm.
Einstein's theory of relativity. It's
Hmm.
also a decent theory. It's not again, it's a better approximation than Newton's theory. So you
Hmm.
can think of the image is like Einstein's theory could be like a source, and it links to Newton's theory.
Yeah.
But you go a little bit more upstream. What's above Einstein's theory? Well, you probably add some quantum. You can quantize. You can add graviton to it. So like Einstein's theory plus plus. Okay, add a little quantum mechanics to it. And
Yeah.
then above that, I don't know. Maybe it's string theory. But string theory, we don't know how to calculate exact stuff yet.
Yeah.
Um, so above that, I don't know. There's some vague notion of an M theory that's kind of the source of the string theory. Maybe
Hmm.
that will give us something.
Hmm.
Um, but so we know that gravity kind of plays well with this space of theory paradigm. It also doesn't in some sense because gravity is one of those theories where the ignorance is a lot harder to control.
Hmm.
And we talked about this before because experimental is because when you measure something, nothing is absolute. So even the
Yeah.
fact that I can, in normal theory, I can say, well, what's the mass of the electron? At least I can measure it. But
Hmm.
at certain energy, you make a black hole. You can't. Um,
Yeah.
that so in some sense, the space of theory gets destroyed at some point for gravity. Maybe it continues somewhere, or maybe this is showing that the space of theory is bunk. It's good
Hmm.
except for gravity. I don't know. I don't have a good answer. But one thing I do know is gravity is interesting.
Yeah, actually, an audience question just came in, which I think ties to what you just mentioned. What if there are arbitrarily high energies in QFT? QFT meaning quantum field theory for those who aren't as familiar with the acronym.
Yeah. So in terms of space of theory, like let's link that to taking a walk in the space of theory. We described
Okay.
before that high energy means you're zooming in, you're getting
Mm,
close to the distance. It meaning that you're being a little picky. Imagine the Lego block city. You're
yeah.
basically like an inspector general. You're like, hey, look, I'm trying to look at this Lego building to see if it's really up to code to like a real building. So I'm zooming in and really examining my theory. And the more I zoom in, the more flaws I'm going to see, right? Um, so so of course, if you ignore gravity, there's a chance that you can always shrink your Lego block to be smaller and smaller and smaller and
Mm,
satisfy the inspector. You'll be like, hey, inspector, guess what? Let me improve my Lego block. And at some point, maybe your Lego block is so small to the atomic scale that it might as well be the real thing. Okay.
yeah.
But there's a limit in gravity, like I said before. At some
Mm,
point, a black hole comes in. So
yeah.
you're kind of stuck. And I don't exactly know if this image of the theory of spaces still makes sense anymore. I mean, maybe it'll still survive on some level, but at the end, yeah. At high energies, usually it's okay for general quantum field theory,
Mhm.
but gravity is the kicker. It messed things up, basically.
Mm, that that makes sense. So we're basically almost at time. I wanted to give you a chance to leave the audience with any, in our tradition, any words of wisdom that, space of theories has taught you in your life.
Right. Yeah. First of all, let me try to answer that question. Does the one theory exist?
Yeah.
Um, I mean, yes and no, right? No, to the extent that we've never seen something like that. We still have no evidence for it. But
Mhm.
yes, to the extent that it's an ideal we like to hold ourselves up to. Um, and it helps us get things along. But so far, it seems like we're not getting there. But
Mhm.
anyway, regardless of the outcome, I would say that um, this discovery of the space of theories, which led to the Nobel Prize because what is it? Kenneth G. Wilson used it to study critical phenomenon, which we described in last episode. It was able to describe water at the critical point and many other substances. So it's helpful to study like different phases, right? Um,
Mhm.
but he does that by embracing this ambiguity of theories and by making connections that to many physicists back in the days would seem kind of crazy. They're like, hey, what are you like this space of theory nonsense? It's like because people think like I said before, it seems like our imagination, right? It's not real physics,
Mhm.
in that way. And some people in the beginning don't like it. Like, hey, look, like I want to calculate the charge of the electron. Who are you to tell me that it depends on my theory? That's crazy. You're crazy, right? But the moment we embrace that, the moment you accept that, hey, look, our theory is not perfect, and but nature is better than us. The moment you humble yourselves, you're able to build these relations, be able to describe things that previously people didn't know were possible. And
Mhm.
I guess the life lesson is that sometimes, like, let go of your ego, kind of the physics ego, whatever you call it, the theoretical ego, and embrace ignorance, the fact that you don't know.
Mhm.
and and maybe when you do that, you actually find out you know a little bit more than if you just say hey, and if you just really try to know. It's better to know that you don't know and try to wrangle with that instead. So I think
Yeah.
that's a beautiful lesson in physics, at least during graduate school, right? Because I always have this fantasy that physics is exact. Like it's like very pure. It's like mathematics. An equation
Mhm.
is an equation. But the moment you learn about renormalization, you're like, bam, physics is not exact. But that's okay. So it's I think physics is great that way. It's okay to be imperfect, and in fact, it's great to be imperfect. It lets you do more.
Yeah, those are some I guess like comforting words that's not exact. That's okay for it not to be exact. So on that note, I want to thank everybody for joining us, and we'll see you all next week.
Yeah. See you all. Thank
Yep.
you.
Bye.
Bye bye.